Good morning, everybody. Today we're going to continue talking about the imines and try to drag in some applications of imine chemistry, something that might be of concern to people that are interested in biochemistry, nutrition, and dietetics. Okay. Last time we were talking about an important reaction that is engaged in by both ketones, aldehydes, carbonyl compounds, and also by imines, and that was tautomerization. So let's just do a brief recap of what we talked about in regard to tautomerization. Recap of tautomers. All right, so we pointed out that what we're looking for is a double bond, a single bond, and then a bond to hydrogen. And this is the unit that undergoes the tautomerization. And so just keeping everything, let's see, a specific example, the most important one would be the keto-enol tautomerization, where you have a carbon-oxygen double bond, and that tautomerizes under either acidic conditions or basic conditions. And the double bond and the single bond change places, and hydrogen appears to jump from the single bond end of the original to the double bond end of the original. So that's the keto-enol tautomeric pair. And we're talking about imines, and imines also do a tautomerization, where once again we identify a double bond. This time it's a double bond to nitrogen, a single bond, and then a bond to hydrogen. And under acidic or basic conditions, the double bond and the single bond change places, and the hydrogen appears to jump from one end of the tautomerizable unit to the other end. So this is the imine-enamine tautomeric pair. Okay, and we talked about how the mechanisms for those reactions. Okay, so that's just a recap of what we talked about concerning tautomerization. Okay. So a lot of people taking this course are interested in nutrition and dietetics, which is a branch of biochemistry. So what I want to talk about is how tautomerization and the chemistry of imines, the impact of those reactions on dietetics, metabolism, biochemistry in general. So maybe you know what an essential amino acid is. Maybe you've heard of that term, essential amino acids. These are amino acids that must be supplied by the diet. They cannot be synthesized by your body. So you have to ingest these in the food that you eat. Amino acids, of course, they are dramatically important in biochemistry because they are the building blocks of proteins, and proteins not only function as structural materials, that's what your hair, your skin, all of your internal organs are made out of, but they are also the building blocks of the enzymes that control all of your metabolic processes. So obviously proteins are important, and the building blocks of proteins are amino acids. Some amino acids can be synthesized by the body. Other amino acids must be supplied by the diet. I want to talk about the non-essential amino acids, how your body constructs amino acids from stuff that is not an amino acid. And you'll see this has a lot to do with imine chemistry and also with the tautomerization. All right, so let's say you eat sugar, right? That's D-glucose. And there is a process called glycolysis. That's the breakdown of sugar. One of the products of the breakdown of sugar is this compound called pyruvic acid. This is pyruvic acid. All right, pyruvic acid is not an amino acid. So this is not an amino acid because, you know, in the term amino acid, I would be looking for a nitrogen atom. So there's no nitrogen atom here. This is not an amino acid. This is one of the products of the breakdown of sugar. Okay, so what we're going to show now is how an amino acid is created from something that is not an amino acid. An amino acid is created actually from sugar. Okay, so you have this molecule. So this is called pyridoxamine, but most people know this as vitamin B6. Okay, so pyridoxamine or vitamin B6. I'm going to erase this because I'm going to need this real estate, I think. Let's just write up here, maybe vitamin B6 gets together with pyruvic acid and you have acid and basic catalysts around. And so what if I were to ask you to predict the product of the reaction? Well, it's a primary amine, NH2, and that's an aldehyde or a ketone. Notice this is a carbon-oxygen double bond, but this is not an aldehyde or a ketone double bond, right? This is a carboxylic acid. So there is no question here of where the reaction will happen. It's going to happen here. But it's the recipe for an imine. You have a primary amine, you have an aldehyde or ketone. These get together to form an imine. Okay, so because this is kind of complicated here, I don't want to keep writing this. So I'm just going to write AR here, standing for aromatic, standing for arene. I guess is what we're calling this, right? And so we get an imine where the carbon-oxygen double bond is replaced by a carbon-nitrogen double bond. So there's the imine that forms. Okay, now this thing undergoes a tautomerization. Oh, I should also point out that water is produced because that's one of the products of imine formation. So this thing has this double bond, single bond, bond to hydrogen, right? There's the tautomerizable unit. So this thing, this intermediate undergoes a tautomerization. I'm going to call that just TAUT, where the double bond and the single bond change places. And the hydrogen appears to jump from one end of the single bond end of the original tautomerization unit to the double bond end of the original tautomerization unit. Okay, so that would be the product of the tautomerization. But what we notice here is what has actually happened is we've gone from one imine, I see that carbon-nitrogen double bond, to a new imine. I see a carbon-nitrogen double bond, but that double bond has changed places. So we've gone from an original imine to another imine. We know that imine formation is reversible, so that if we add water and acid to an imine, and is there any water inside your body? Oh my heavens, yes, you're 95% water. Are there acids and bases available in the physiological system? Oh my heavens, yes, because this is what one of the roles that the enzymes are performing. And so since this is an imine, we add water to it and enzymatic acids and bases, and we can reverse the imine formation. So we get this carbon-nitrogen double bond reverts to a carbon-oxygen double bond, and the imine nitrogen departs as a primary amine nitrogen. Okay, so this is just the reversal, the hydrolysis of imine formation. But what has happened here, and this is the point of what I'm talking about, is that this is an amino acid. This is alanine. This is one of the non-essential amino acids. Your body can make this from pyruvic acid, whose ultimate source is the sugar that you eat. So this is alanine. This is an amino acid. And this sequence of reactions shows how an amino acid, by imine formation, tautomerization, and then reversal of the imine formation, can be created. Ordinarily, you're getting all of the alanine that you need from the diet, but if you're starving, if your diet is low in alanine, your body can create all of the alanine that it needs, as long as it has this vitamin B6 to deal with. Okay, so we have this aldehyde here, and so going to show a little bit later, if we have time, what happens with this aldehyde here and how we can go back from here to there. Okay, so let's try this again, just for fun and practice. All right, so once again, beginning with the vitamin B6, right? That's the vitamin B6. And this time, maybe in one of your other courses, you've heard of the citric acid cycle. The citric acid cycle is one of the three main energy-producing biochemical processes in your body. The other two being glycolysis, that's the breakdown of sugar. You get calories, you get energy by the breakdown of sugar, that's glycolysis. Then we have the citric acid cycle, you get energy out of the citric acid cycle as well. And then the third is oxidative phosphorylation, which are all of the biochemical reactions that involve ATP. Maybe you've heard of ATP in one of your other courses. That's one of the energy producing processes. Okay, so the citric acid cycle produces this guy. This is called alpha ketoglutaric acid. And it's not an amino acid. I don't see any amines in here. This is not an amino acid. This comes from the citric acid cycle. But what I see here is the recipe for imine formation. I see a primary amine. I see a bunch of carbonyls here, but imine formation is a reaction of aldehydes and ketones, not of carboxylic acids. That's a carboxylic acid. That's a carboxylic acid. These do not form imines. It's only an aldehyde or a ketone. So this this ketone functionality here gets together with the primary amine. We get the imine. which would have this structure.
And now, just like in the example we saw before, we see that this molecule can undergo a tautomerization,
where we have a double bond, a single bond, and a bond to hydrogen. So water is produced here. This thing tautomerizes. The double bond and the single bond of the tautomerizable unit change places.
and we've gone once again from a imine to a new imine. Imine formation is reversible, so that the addition of water and enzymatic acids are going to break up this imine bond. The imine carbon will revert to a carbonyl carbon, and the imine nitrogen will revert to a primary amine nitrogen.
So let's picture all of that. So there's our carbonyl group. There's our primary amine.
So what has been created here is another non-essential amino acid derived from something that was not an amino acid.
And this is called glutamic acid.
And have you guys ever heard of this sensory perception called umami? Maybe you heard about that. Yo mama, umami.
Well, foods that
are high in glutamic acid, they have a supposedly delicious and savory taste, and that is due to the high concentration of this amino acid, glutamic acid. Maybe you've heard of something called monosodium glutamate. Well, this is a flavor enhancer that is put into food to make it taste better, because glutamic acid, this tastes very, very good to most people. And what is the food that is highest in glutamic acid by weight? What would be the food that has more glutamic acid than anything else? Okay, so I'm going to try to show you some pretty pictures of glutamic acid. Pray for me. I hope this works. Yeah, right here. So umami, right? Lots of glutamic acid. That's found in soy sauce and in sunflower seeds and in seal meat. Anyone ever had seal meat? I guess it must taste very good, because that is the meat that is highest in glutamic acid by weight, right? When you're eating a seal, you're eating seal muscle or organ. I apologize to anyone here who is a vegetarian or vegan. And so this seal meat has more, the proteins that make up seal meat have more glutamic acid than anything else. All right. So any athletes out there? I know at this time it's very hard to work out in the gym, but maybe you like to pump iron, and you're lifting weights all the time, or that's part of your fitness regimen. If you're trying to build muscle, one of the things that you're usually told to do is eat a lot of protein, eat a lot of high protein shakes and so on and so forth. Well, it turns out that even if you are eating a whole lot of protein, you still can't assimilate all of the protein that you eat because your body has feedback regulation mechanisms that dispose of excess protein. Your body is looking to ingest a certain amount of protein. If you give it too much, there's no way of storing that protein. What it's going to do is it's going to degrade that protein, and it's going to just use that molecule for some other purpose. So this is a process that is called deamination of an amino acid, and this is one of the pathways that your body deals with excess protein. If you are just eating straight protein, you can't absorb it all. There are shut-off mechanisms. Your body is just getting too much protein. There's a way of disposing of it. So I want to talk about that now. Deamination of an amino acid, which is how the body deals with excess protein. Okay, so you get protein, and how protein is metabolized is that, for example, you eat a hamburger or tofu or whatever, and your body breaks down that cow protein or that soybean protein to a bunch of amino acids, and then it builds those amino acids back up to a human being protein. So the protein is broken down to an amino acids. But as I'm saying, if you're ingesting too much amino acid, then you have ways. The body has ways of tearing down that amino acid, and that's deamination. Okay, so remember we were talking about that vitamin B6, and we saw that the end product of creation of an amino acid from something that was not an amino acid was an aldehyde. So we gave it this structure. All right, and so now demonstrating with an amino acid here, right? This is alanine. This is an amino acid. And let's say you've eaten too much alanine. So what does so can you absorb all of it? No. So now this guy, remember, he was the product of the creation of an amino acid. Now he's going to get involved in the destruction of an amino acid. It's a recipe for an imine. You have a primary amine, you have an aldehyde or ketone. These two get together. They expel a molecule of water, and the carbon-oxygen double bond is replaced by a carbon-nitrogen double bond. And so we have this imine here. And now we see an opportunity for a tautomerization. We have a double bond, a single bond, and a bond to hydrogen. So this tautomerizes once again, and the double bond and the single bond change places. Whoops. The double bond, terrible. The double bond and the single bond change places, and the hydrogen jumps from one end of the tautomerizable unit to the other. And as we've said before, the imine formation is reversible, so that if we add water and enzymatic acids or bases to this, we can tear the imine down. And when we do that, here we're going to get there's our pyridoxamine back again, right? If you look back at your lecture notes, if you look back at what what we said a couple of minutes ago, this is what is used to create an amino acid from something that is not an amino acid. So this vitamin B6 is a catalyst. And over here we get something that is not an amino acid. This is back to being pyruvic acid, which we talked about a few minutes ago. So these are the sequence of chemical events by which an amino acid is torn down into something that is not an amino acid. And this molecule here, pyruvic acid, oh, this is a powerhouse molecule for your body because this is a source of energy in the citric acid cycle. So this is the sequence of events that happen with the deamination of an amino acid. Okay. So now what I want to do is draw the curtain on the aldehyde and ketone chemistry and move on to another topic, another family of reactions. But before I do that, any questions about anything? Anything anyone want to bring up? All right, so we have to get back to homework. So I'm going to be publishing a homework problem set that's going to be due Friday of next week. And that's going to be all about imines. So I'll send a message to the class alerting you about when that homework is due. It's going to be due next Friday of next week. All right, so now let's take up another family of reactions, a huge family of reactions that are extremely important in organic chemistry and also in biochemistry. And this is acyl substitution. So it's appropriate that we talk about this now because, you know, we just talked about acyl a minute ago and how acyl would be the most delicious thing you could eat because its flesh has more glutamic acid by weight than any other meat, right? So we're still talking about acyl, but acyl is spelled this way now, A-C-Y-L. Okay. Acyl substitution is a reaction that is engaged in by acyl derivatives. And so what we're doing here is we're going to look for an acyl derivative. And an acyl derivative is a carbonyl compound. Has a carbonyl group in it, but this carbonyl carbon is bonded to something that is not carbon and not hydrogen. So I'm going to call that Z, and I'm going to point out that whatever this thing is, whatever this atom is, cannot be carbon or hydrogen. And so I've said something that's very important here, and I said something that's going to be the downfall of many people. Is that in one box over here, you have your aldehyde and ketone reactions. That's hydration, that's hemiacetal formation, that's acetal formation, that's imine formation, blah, blah, blah. It's all of those reactions of aldehydes and ketones. Aldehydes and ketones have carbon or hydrogen on both sides of the carbonyl carbon, right? That's not what we're talking about anymore. Now we're talking about acyl substitution where the carbonyl carbon is bonded to something that is not carbon and not hydrogen. So it's very important for you to keep straight what is an aldehyde or ketone reaction and what is not an aldehyde or ketone reaction, what is an acyl substitution reaction. Okay, so this thing that I'm calling Z cannot be more carbon or more hydrogen. So what can it be? Well, it can be halogen, right? Or it could be oxygen, or it could be nitrogen, or it could be sulfur. It could be a lot of things, just not more carbon and hydrogen on both sides of the carbonyl. Let's look at some specific examples of acyl derivatives. All right, so a specific example could be.
Wait, can the other side be bonded to a C or an H?
It can.
Okay.
All right, so let me just give you some specific examples. Something like this. Okay, so there's a carbonyl carbon, right? It's bonded to carbon on one side, but an acyl derivative is not going to be bonded to carbon and hydrogen on both sides. So right here, I'm going to put a Cl. That's an acyl derivative. You're looking for a carbonyl carbon that is bonded to something that is not carbon and not hydrogen. This is called an acyl halide, or in this case, an acyl chloride. Okay, more specific examples. How about let's put oxygen there. There's the carbonyl carbon, but now I'm going to tie up that carbonyl carbon to something that is not carbon and not hydrogen. See this carbonyl carbon here? It's bonded to oxygen. This is an acyl derivative. See this carbonyl carbon here? It's bonded to something that's not carbon and not hydrogen. This is called an anhydride. Okay, more specific examples of an acyl derivative. Something like, okay, now I'm going to put maybe a benzene ring here. Sure, why not? The carbonyl carbon is bonded to carbon on one side, but on this other side, it's bonded to something that is not carbon and not hydrogen. This is called a thiol ester, right? If this sulfur atom were an oxygen, it would be an ester. But this, I replace that oxygen in the ester with the sulfur, I get a thiol ester. These are very, very important in biochemistry. All right, so what about the regular ester? See, there's a carbonyl carbon. It's bonded to hydrogen on one side. But on the other side, I'm going to bond it to something that is not carbon and not hydrogen. I'm going to tie it up with an oxygen atom. This is an ester. This is an acyl derivative. Okay, so that's an ester. More specific examples of acyl derivatives. I could also have a carboxylic acid, where I'm going to have, say, a OH, a carbonyl group, a carbonyl carbon that's bonded to something that's not carbon and not hydrogen. That's another acyl derivative. How about switching over to a nitrogen? I could have an amide, something like this, right? That's an amide. That's another acyl derivative. It's carbonyl carbon bonded to something that's not carbon, not hydrogen. You'll hear me repeat that 100,000 times because I want to make it crystal clear that we have a box in which the aldehyde and ketone reactions live. Now we're going to have a box where the acyl derivative reactions are going to live, and they're not the same, right? Just because something has a carboxylic, just because something has a carbonyl group in it does not mean that everything with a carbonyl group can form an imine. Just because something has a carbon-oxygen double bond in it does not mean that that thing is going to form a hydrate. You have two boxes now, the aldehyde and ketone box and the acyl derivative box. It's very important to keep them straight. Okay, so, wow, that's a lot of stuff, right? That's millions and millions of compounds. That's the acyl substitution is something that can happen to anhydrides, acyl halides, esters, thioesters, amides, lots of stuff. This is gigantic, gigantic family of reactions. But the unifying theme is you're looking for a carbonyl carbon that is bonded to something that is not carbon and not hydrogen. Okay, so these are the kinds of molecules that can do this acyl substitution reaction. All right, so let's get into acyl substitution. The reaction can happen under acidic conditions, neutral conditions, and basic conditions. So we're probably going to concentrate mostly on acidic conditions, but we'll have to talk about basic and neutral as well. Okay, so let's talk about acyl substitution, overall reaction. RXN means reaction in acid. So here's our acyl derivative, right? I'm just keeping everything very general because although millions, tens of millions of compounds can do acyl substitution, the unifying theme is a carbonyl carbon bonded to something that is not carbon and not hydrogen. Okay, under acidic, this is the electrophile. Of course it is, because for weeks and weeks now we've been talking about how a carbonyl carbon is an electrophile. It is attacked by nucleophiles. The nucleophile in acyl substitution in acidic conditions, the nucleophilic atom is going to be protonated. It's going to have a proton on it. So I'm just going to represent that by H nuc, right, where the nuc represents the nucleophilic atom. Now, not every atom in the nucleophile is the nucleophilic atom. Every nucleophile has usually one nucleophilic atom. And so what this means is that the proton is on the nucleophilic atom. The reaction is reversible. We're talking about the reaction under acidic conditions. And so what happens here is the thing that is not carbon and not hydrogen that breaks off, it takes off. The nucleophile takes the place of this departing Z group that is the nucleophile minus the proton that it rode into town with. Okay, so in acyl substitution, the thing that is not carbon and not hydrogen goes away, and the nucleophile minus the proton that it entered into the reaction with takes its place. This guy goes away, it's a leaving group, and in a formal sense, it departs with that proton that the nucleophile came in with. So if I put maybe a little dot here around here, you can see there's the remnant of the nucleophile. But when we go through the mechanism of this reaction, we'll see that if this guy is Fred, if this proton is named Fred, this is not Fred here. This is Mary, this is Sally, this is somebody else. It just looks like Fred came in on the nucleophile, and it just looks like Fred departs with the leaving. Okay, so that's the overall reaction, very generic nucleophile of acyl substitution. Let's do some specific examples. Okay, so what about if we have, let's say we have this ester. Oh, something even better. Something even better. Okay, there's a carboxylic acid. It's an acyl derivative. I see a carbonyl carbon that's bonded to something that's not carbon, not hydrogen. And now let's put in the nucleophile. Right, this is the nucleophile, right? But not every atom in the nucleophile is the nucleophilic atom. This, the nucleophilic atom here is this oxygen atom, because that's the only atom that has electron pairs. That's the only atom that is electron rich that can function as a nucleophile. Okay, what if we were to add a squirt of acid? What would we get? The thing that is not carbon and not hydrogen goes away. The nucleophile minus the proton on the nucleophilic atom takes its place. See how I kicked out this OH? And see how I brought the nucleophile in? And I got rid of the proton that was on the nucleophilic atom? This proton, in a formal sense, pops out with the departing leaving group. So this is just kind of a baby way of writing water, right? So this is an example of this acyl substitution, acidic conditions. Anybody recognize this reaction? Does this look at all familiar? That's the banana oil reaction, right? This is isopentyl acetate. This is the banana oil stuff that you made. So this is an acyl substitution reaction. Okay, so let's see. We're going to have plenty more examples, but before time runs out, let's write the mechanism of the reaction.
I have a quick question about
Yes,
the
go ahead.
derivative. So I know it can't be bonded to a C or an H on one side, but what if it was bonded on both sides to like Z? Which one would you then pick to?
Oh, we will have a lot to say about that later. So
Okay.
what you're asking me is something like this, I guess, right? So I'm going to tie up this carbonyl to something that is not carbon and not hydrogen on one side.
Yeah.
I'm going to put something that's not carbon and not hydrogen on the other side. Is that what you're asking me?
Yeah.
Oh, we'll talk a lot about what happens here.
Okay. Thank you.
Let's hold on. All right, so let's talk about the mechanism in acid. All right, so I'm going to, because tens of millions of compounds can do an acyl substitution, I just think it's best to keep everything very general here. And because I definitely want you to remember that Z cannot be carbon and cannot be hydrogen, right? It can be a lot of things, as we just talked about. But it's a carbonyl compound. It's sitting around in acid. What are the first two steps of the mechanism? Correct. Protonate the carbonyl oxygen and then attack the carbonyl carbon with a nucleophile. This is one of the themes that we see repeated. Okay, mechanism in acid. First step, protonate the carbonyl oxygen. And then attack the carbonyl carbon with the nucleophile. So it's very important for you to be able to identify what the nucleophilic atom is in the nucleophile, right? Because just not every atom is going to be the nucleophilic atom. So we're looking for something that has an electron pair, or maybe something that has a negative charge. It's not going to be just every atom or any atom in the nucleophile. Protonate the carbonyl oxygen. Attack the carbonyl carbon with the nucleophile. We've seen these two steps a gazillion times before. So notice how the nucleophile has attacked in an intact sort of way. That proton that the nucleophile has on it is still there. And I have to draw this positive charge on whatever this nucleophilic atom is. Okay, and now, just like we saw with the acetal and with the imine, there's a lot of fiddling and diddling with protons, because what has to happen is this Z group has to go away. So how does it go away? Well, this guy undergoes a deprotonation. So a base in the solution comes along and removes that proton. So we get this intermediate. And now, so that's Fred, right? He's gone. He goes into the solution. Never heard from again. But there are a lot of other protons in the solution. One of them maybe is Mary, or one of them is Sally. Now Sally comes in, and this Z group, remember, what can this be? This can be a halogen. A halogen has 1, 2, 3 unshared pairs of electrons on it. It could be an oxygen. An oxygen has 2 unshared pairs of electrons on it. It could be a nitrogen. A nitrogen has 1 unshared pair of electrons on it. It could be a sulfur. A sulfur has 2 unshared. Whatever this thing is, it's going to have an unshared pair of electrons on it, which is what this Z group uses to eat up a proton, eats up Mary in solution. Okay, so these last 2 steps, this is just a lot of fiddling and diddling with protons. Now, whatever Z is here, chlorine, highly electronegative, oxygen, very electronegative, nitrogen, very electronegative, whatever this is, it doesn't like to have that positive charge, because this is typically going to be a pretty electronegative atom. So again, this is a step that we've seen repeatedly, is that this bond is going to break. This bond is going to break, and that highly electronegative Z atom, in order to get rid of that positive charge, is going to eat up this electron pair. And there's our departing Z group, right? Because remember, we said that the Z is going to break off. It's an equilibrium. That Z group is going to break off, and what is left here is this carbocation intermediate. And now the last step is going to be the deprotonation of that oxygen and the reformation of that carbon-oxygen double bond. So a base comes along, removes that proton. The reaction is catalyzed by acid. A proton got the mechanism going, but a proton is spat out at the end of the reaction, and that brings our reaction mechanism to a close. Right, so what has happened here is the thing that's not carbon, not hydrogen, has broken off. It took off with, it looks like it took off with the proton that the nucleophile came in with. But we just see in this mechanism that that's just, looks are deceptive. That's this proton here is not the proton here. Okay, so that's the mechanism, acyl substitution in acid conditions. Okay. So let's go back to product prediction. How about something pretty complicated? All right, so maybe you don't recognize the structure, but it's something you've all heard of. Before DNA came along, this molecule was the most heavily researched molecule in world history. Now DNA is the most heavily researched molecule, but before DNA, this one. And what is this? Penicillin. Right, you heard of that, right? Antibiotic. So what if you were to take penicillin and you were to react that with an excess of water under acidic conditions and heat it? Draw the structure of the products. You're going to get more than one product. Let's see if we can figure out what the products of this reaction is going to be. What are you looking for? An acyl derivative. You're looking for a carbonyl carbon that is bonded to something that is not carbon and not hydrogen. The thing that is not carbon and not hydrogen is going to break off. The nucleophile minus a proton is going to take its place under acidic conditions. Okay, so first thing, you're shopping around for an acyl carbon. There's a carbonyl carbon bonded to something that's not carbon and not hydrogen. This bond is going to break, and this whole molecule is going to take off. The nucleophile, which is water, HOH, you know how water is HO, HOH? So HO comes in, and the proton appears to go away with the exiting leaving. So that would be one of the products. The other product would be, see, this is the proton that in a formal sense, but not in actuality, came from water. Okay, so those would be the two products of this first step. But is the reaction over? Oh no, because here I see another acyl carbon. I see a carbonyl carbon that's bonded to something that's not carbon and not hydrogen. This bond is going to break, and the thing that is not carbon and not hydrogen is going to take off with the extra, it looks like with the extra proton that the nucleophile came in with. So I'm putting him in brackets. He's not going to be around very long because I have excess water, and so the reaction can keep going. The thing that is not carbon and not hydrogen broke off, and the nucleophile has taken its place, minus the proton that it rode into town with. But this nitrogen atom has not left the molecule. It has left the acyl carbon. It hasn't left the molecule because it's still tethered to the molecule by other bonds. So it would be wrong to just somehow break this whole half of the molecule off, because this nitrogen atom is still bonded to the molecule by other bonds. And here I see the remnant of the water molecule. Okay, so that's important to realize, that when the thing that's not carbon and hydrogen breaks off, what it is breaking off from is the acyl carbon, not necessarily from the molecule as a whole. Okay, so are we done? Is this the product? Well, here's another acyl carbonyl. I see a carbonyl carbon that's bonded to something that's not carbon and not hydrogen. This is an acyl carbonyl as well. I see a carbonyl carbon bonded to something that's not carbon, not hydrogen. However, when this reacts with the nucleophile water, the leaving group, OH, is going to be the same as the entering nucleophile, also OH. So acyl substitution is still happening, but no new compound is being created because the thing that goes away, OH, would be the very same thing that would be coming in, also OH. So this thing isn't dead in the water. At a microscopic level, acyl substitution is still happening, but that reaction doesn't lead to the formation of anything new. It's just the same as the starting material. Okay, so this would be a final product, and this would be a final product of this hydrolysis of penicillin. Now, why would anyone want to take penicillin and boil it in acid and water? Destroy a good molecule of penicillin, especially now when we need antibiotics. Well, I don't know why anyone would want to do that, but maybe you have heard of penicillin-resistant bacteria. These are superbugs, they're usually called, that cannot be killed off by penicillin. How does a penicillin-resistant bacteria, what makes it penicillin-resistant is that it has an enzyme called penicillinase that catalyzes this reaction. It takes penicillin. Is there any water in a bacteria? Oh my heavens, yes. Is there acid in a bacteria? Yep, that's what penicillinase, that enzyme, is providing. And so penicillin-resistant bacteria, they get that way because they have an enzyme that can kill the penicillin molecule according to this acyl substitution reaction. Okay, so next time we'll be talking more about acyl substitution. We'll be on this topic for a couple of weeks, I think. So before we sign off, any questions about anything? Anybody come up with something?
When will the other recorded lectures be put up on your YouTube?
I'll try to work on that today. I haven't uploaded Mondays, I think. Yeah, I'll work on that today.
Thank you.
Okay, anything else?
Oh, you said the homework would be posted today?
Yeah.
Okay, thank
And
you.
it'll be due Friday of next week. It's going to be all about imines and tautomerization.
Okay, and that's just on grade scope, right?
Yes.
Okay.
Anything else? All righty, I'll see you next time. Bye-bye.